Welcome to the deep dive. We sort through the noise to bring you some clarity, some insight on really fascinating topics. Today, we're looking at classic science fiction. You know, those huge, epic journeys across galaxies, or talking instantly across light years, even transforming dead planets into, like, new Earths. These ideas are huge, right? They're not just background noise, they really shape how we imagine the future. So let's unpack this. Our mission today is a deep dive looking at this great article from Explorer's Web. It's called Classic Sci-Fi Tropes, Fact or Fiction. We're going to explore these big physics ideas from sci-fi and figure out, what's pure fantasy and what might actually be closer to science than you think. It's your shortcut to getting up to speed on some really cool science and fiction crossovers.
Exactly. And we'll break down three big ones: faster than light travel, instantaneous communication, and terraforming. We'll look at the science we know now, what the laws of physics actually say about whether these things are even possible. We'll give some context, talk about the implications. What's really fascinating, I think, is seeing how close some ideas get to reality and how others are just spectacularly far off for now.
Okay, let's start with the big one. Faster than light travel, FTL. It feels essential for most space sci-fi. But why, though? Why is it so fundamental? Can't we just use light speed?
Well, is it the distances? They're just mind-boggling. I mean, even going at light speed, getting to the nearest star, Proxima Centauri, that's over 4 years. And crossing our own galaxy, the Milky Way, you're talking 100,000 years. So imagine the Starship Enterprise or the Millennium Falcon stuck at light speed. Journeys would take lifetimes, generations even. Your characters, they'd grow old, they'd die between planets. For storytelling, it just doesn't work. FTL isn't just convenient. It's basically required to make things like galactic empires or exploring new worlds happen in a human lifespan.
Makes sense. So authors get creative, really creative. We see things like hyperspace or wormholes. George Lucas, Douglas Adams, Martha Wells, C.J. Cherryh, they all use these ideas. They're like these magic shortcuts for those huge adventures.
Right. And what's interesting is that wormholes and even the basic idea of hyperspace, like another dimension, aren't totally pulled out of thin air. They actually pop up as theoretical possibilities in Einstein's general relativity equations, the ones describing gravity as space-time bending. So mathematically, these kinds of shortcuts are allowed.
Okay, so the math says maybe. But what about actually using one? Can we just, pop through a wormhole?
That's where it gets tricky. While the equations allow them, more detailed calculations suggest, well, probably not. They'd likely be incredibly unstable.
Unstable how?
Like they'd collapse the instant anything tried to go through, even a single photon. Some physicists even think a more complete theory of gravity, one that includes quantum mechanics, might rule them out entirely, like the universe has a built-in no shortcuts rule.
Stops paradoxes, maybe.
Perhaps. And maybe that's a good thing, because the fictional idea of FTL going wrong, it can be pretty terrifying. C.J. Cherryh wrote this book, Port Eternity. It describes this eldritch horror scenario, getting stuck in hyperspace. Ship just drifting forever, weird things knocking on the hull.
Okay, that's genuinely creepy, being lost outside reality itself. But then you've got Star Trek's approach. The warp drive, specifically the Alcubierre drive concept, feels a bit more grounded.
It does seem closer, yeah. It was posed by a real physicist, Miguel Alcubierre. The idea is clever. You compress space in front of the ship and expand it behind. So the ship itself, in its local bubble of space, never actually goes faster than light. It's the space around it that's moving. It neatly sidesteps breaking general relativity.
Take that, Star Wars. So it works on paper.
Conceptually, yes. It fits within Einstein's laws. The huge problem, the major hurdle, is the fuel. The Alcubierre drive would need something called negative mass or exotic matter.
Negative mass? What even is that? Like anti-gravity?
Sort of, yeah.
Yeah.
Hypothetical stuff that would push things away gravitationally instead of pulling them in. Most physicists, they really doubt it exists. It would kind of rewrite our understanding of energy and gravity. It's not just an engineering challenge. It's a fundamental physics question.
So we don't even know if the required fuel can exist. That's a pretty big roadblock.
It's a huge one. It needs a whole new kind of physics, not just better engines.
Okay, so FTL travel seems unlikely for now. Even the clever Star Trek version has massive issues. What about talking faster than light, though? FTL communication. Because even writers who stick to slower than light travel, like in the Bobiverse books or the Three-Body Problem or parts of Ender's Game, they often still use FTL communication. That idea of instant chats across the stars is just too tempting for stories, I guess. Is physics going to shoot that down too?
Afraid so. The laws are just as strict about sending information faster than light as they are about sending spaceships. FTL communication, also a no-go. Light speed isn't just a limit for matter. It's the ultimate speed limit for information, for causality itself.
But hang on, what about quantum entanglement? That's the one everyone brings up, right? Einstein's spooky action at a distance. It sounds like instant connection.
Ah, yes, entanglement. It's real, it's weird, but it's probably not useful for communication.
Okay, explain. What is it exactly?
It's when two particles get linked in a deep way. They share the same fate, no matter how far apart they are. Imagine, say, an atom decays and spits out two particles with opposite spins. One spins up, the other spins down. If you measure one particle way over here and find it spinning up, you instantly know the other one, even light years away, must be spinning down. That correlation looks instantaneous.
Right. I remember John Stuart Bell's analogy about his colleague Reinhold Bertelsmann and his socks. How Bertelsmann always wear mismatched socks. If you saw one sock was pink, you instantly knew the other wasn't pink.
It's a great way to grasp the correlation aspect, yeah.
Yeah.
But there's a key quantum difference. Unlike socks, quantum states can be random until measured. The entanglement means if one particle randomly settles on spin up when you measure it, the other instantly becomes spin down, and vice versa. It's not predetermined like socks in a drawer. And this isn't just theory. We've entangled photons, electrons, even tiny diamonds in labs. It definitely happens.
Okay, so if measuring one instantly affects the other, why can't we send a signal, like that Theseus thought experiment? Theseus has one particle, his dad has the other. If Theseus survives the Minotaur, he measures his particle, boom. His dad's particle instantly changes, signaling he's alive. Sounds like FTL Morse code.
It sounds like it should work. It's a really common thought.
Yeah.
But this is where something called the no-signaling theorem kicks in. It mathematically proves you can't use entanglement for FTL communication. The key is randomness.
Randomness.
Yeah. When you measure your particle, you can't choose whether it collapses to spin up or spin down. It's random, like flipping a coin. So while the other particle instantly takes the opposite state, you couldn't force your particle to be up to send a 1 or down to send a 0. You can't encode information. Any attempt to use it breaks the entanglement itself or is just drowned out by the inherent quantum randomness. It's like having a super fast carrier pigeon that drops dead if you tie a message to its leg.
Huh. So the universe has this built-in protection against sending information faster than light. It keeps causality safe, I guess. But wow, that's a definite no on the instant space calls.
Seems to be a fundamental limit as far as we understand physics today.
Okay, strict rules on speed limits then. Let's switch gears completely. Terraforming. This is that ultimate sci-fi dream, right? Taking a dead rock and making it Earth-like. Like the Genesis device in Star Trek II, bam, instant forests and oceans. Total planetary makeover.
Well, the idea itself isn't pure fantasy. It connects directly to real science, specifically astrobiology. When we ask, how does life start? How rare is it? What does it need? It naturally leads to thinking, well, could we make a place habitable? Could we kickstart life somewhere else? It's a way to test our understanding of life's requirements.
Okay, so where would we start? People always talk about Mars. There were ideas about, like, breeding special microbes.
Exactly. Early ideas focused on engineering microbes that could survive Mars's harsh conditions, maybe produce oxygen, pave the way for algae, that sort of thing. A very slow biological approach.
Sounds plausible, if slow. But Mars has bigger problems, doesn't it? Something fundamental.
It does. The absolute showstopper. Mars has no global magnetic field. Earth does, and it's crucial.
Why is that so important?
Our magnetic field acts like a giant shield. It deflects most of the dangerous cosmic rays and charged particles from the sun, the solar wind. Without it, that radiation slams into the atmosphere, strips it away over time, and bombards the surface.
Ah. So any atmosphere you build up would just get blasted away, and the radiation would sterilize the surface.
Pretty much. Life as we know it would have a really hard time. You need that shield.
So game over for Mars terraforming, or are there crazy sci-fi-like solutions?
Well, never underestimate physicists. One team actually proposed creating an artificial magnetic field for Mars.
Seriously? How?
The idea involves putting a giant superconducting wire loop into orbit around Mars. We're talking a radius of maybe 3,400 kilometers. Then run a huge current through it.
Whoa, that sounds immense.
Oh, it is. The scale is staggering. They calculated it would only require mining about 0.1% of Olympus Mons, the biggest volcano in the solar system, for materials.
Only 0.1%. Right. Okay, so theoretically possible maybe, but utterly monumental.
Exactly. Both the microbial approach and the magnetic field idea are potentially feasible, scientifically speaking, but neither is anything like that instant Genesis device. Getting algae started might take decades. Real forests, maybe centuries, and immense, immense effort and resources. It's a project for generations, not a quick fix.
A truly long game. So terraforming another planet is probably not happening soon. There is no planet B, right? But this makes me think, are we kind of doing terraforming already, but right here on Earth in smaller ways?
That's a really interesting point. Yes, in a sense, it falls into the category of geoengineering. Scientists are experimenting with things like spraying salt-based aerosols into the atmosphere to reflect sunlight and cool specific area. There have been successful tests, and one project is actually deploying this over parts of the Great Barrier Reef, trying to reduce coral bleaching by slightly cooling the water surface. It's a localized attempt to tweak the climate, to manage our planet's environment.
Wow. It sounds like something out of, I don't know, The Hitchhiker's Guide to the Galaxy. Remember those planets they built with engines sticking out?
Huh. It does have that vibe, doesn't it? These aerosol sprayers. But the crucial difference is this is real. And it's happening on Earth, our only Earth.
Yeah.
It really underscores that we're already impacting the planet on a huge scale, and now we're contemplating actively managing it. That comes with huge responsibilities and risks.
Absolutely. Okay, so we've covered a lot. We went from FTO travel, the Alcubierre drive, potentially working but needing impossible fuel.
Right, to FTL communication being a definite no-go, thanks to quantum physics and the no signaling theorem.
And finally, to terraforming may be possible over vast timescales with incredible effort, but we're already doing mini versions here with geoengineering. It's quite a journey from pure sci-fi to the edge of reality.
It really is. And thinking about this stuff matters, I think. Sci-fi pushes our imagination, inspires us to think big, which is great, but understanding the actual scientific limits, that gives us a much clearer, more grounded view of the universe and our own capabilities. It helps us sort hope from hype. Applying that critical thinking is so important today with information coming at us from everywhere.
Couldn't agree more. So for everyone listening, what does this all mean for you? Maybe think about how knowing these limits or possibilities changes how you see your favorite sci-fi. Does the Alcubierre drive seem cooler now or more frustrating? Or maybe it makes you think about our real-world challenges like climate change, realizing we're already engineering our planet, whether we meant to or not. What other sci-fi ideas do you wonder about? Which ones feel real and which feel like pure magic? Something to ponder.